Hello, this is week 2 on surface area and volume. You need to go over to the week 12 content area and download and probably print out the instructor notes, the slight stretch example, the week 12 examples, and the week 12 similarity examples. First thing I'd like to do is talk about the 3 different heights in a pyramid. So I'm going to turn it back over to my camera. Here we have a pyramid. The base of this particular pyramid is a square. The pyramid does not have to have a square base, but this is a square-based pyramid. And this is the top vertex here. We have 3 types of heights. The height, or the main height, is this one on the interior here that's labeled with the green sticky note. And this height right here is going to be needed to find the volume. This slant height out here that's labeled with the pink sticky tab is the slant height, and it is on the surface of the triangular face, and it is needed to find the surface area. The reason it's needed to find the surface area is because it's the height of a triangle, and to find the area of a triangle, we need the height. And finally, there's the edge height, which is this one with the orange sticky tab. And we have 4 versions of this coming from the vertex at the top to the corner of the base. And you might take a look and see of these 3 heights, which one is the longest, which one is medium-sized, and which one is the shortest. That's useful to think about. And you also might look at some of the Pythagorean relationships we have here. So we actually have 6 key links here. We have the 3 heights. Down here in the base, if you look at this, we're going to primarily be working with regular bases. In other words, bases that are equiangular and equilateral. And this particular example is a square, of course. And this distance right here, from the corner of the base to the midpoint of the base, that's half of a base edge. This is going to be a useful length. This distance right here, from the center of the base out to the midpoint of a side, is called the apothem. And this distance right here, from the center of the base to a vertex, is called the radius. And so you'll notice a right triangle down there as well. I highly recommend getting yourself a pyramid and trying to get a feel, literally and mentally, for all these locations. Because when we have a 2-dimensional diagram, it's often hard to visualize the right triangles. So let's visualize the right triangles and the Pythagorean theorem. So down here in the base, I have a right triangle with the radius as the hypotenuse. If you look at the notes from week 12, I have the 4 Pythagorean relationships listed there. And the first one is apothem squared plus half of an edge squared is equal to the radius squared. The second one is on a triangular face. Slant height squared plus half of an edge squared is equal to the edge height squared. This edge height is a hypotenuse for the face triangle. Then we have 2 more examples of right triangles on the interior. The first one is apothem squared plus the height squared is equal to the slant height squared. The height on the inside here will never serve as a hypotenuse. but the slant height can serve as a hypotenuse. And the last Pythagorean relationship uses this Pythagorean, or this right triangle. Radius squared plus the height squared is equal to the edge height squared. I'm not sure how easy this is to see on the video. It's best to see it in person. Now I'd like to turn to the week 12 example handout. In the first example, we have a square-based pyramid, and we have that 16 is the base edge. It's a square with 16 on each side. And the height of the triangle is 24. The arrow in this particular graphic is a little bit off, but it is the regular height, not the edge height. We see the Pythagorean relationship using the apothem, the height, and the slant height. We're using the script letter L for the slant height. So our Pythagorean relationship, well, first of all, we need to get the length of the apothem. The length of the apothem is half of the 16, which is 8. So one leg is 8, the other leg is 24, and the hypotenuse is the slant height, which is L. You see the Pythagorean relationship on the screen, and we do the little bit of algebra, take the square root of both sides, and we get the square root of 640. Now what I'd like to do is to calculate the surface area and volume. So now we need to get out our formula sheet. So you need to have the Wisconsin Mathematics formula reference sheet in front of you, and we're going to be using the right pyramid formulas. The slant height is needed to find the surface area, and the regular height is needed to find the volume. So we're ready to find both of these. Just as a point of showing a good example, I'm going to draw my base here. Now this is pretty trivial in this case, but it won't always be trivial. So this is the base, and capital B is used for the area of the base, so it's going to be 16 squared, which is 256. Now you don't have to write that down if you don't want to, but if it's something like a triangle or a hexagon, you should write it down. I highly recommend that you write down the formula before you plug into it, and I recommend that you have your students do that. We usually plug in more correctly when we do that, and it helps us learn the formulas. So area of the base here is 256. The height was 24. Now run that into a calculator. And we get 2,048 units cubed. This is our volume. Now we're going to find the surface area. So let's see what our surface area formula is. Surface area of a right pyramid is the area of the base plus 1/2 PL. P is the perimeter of the base, and L is the slant height. So we write down our formula first, and then we plug in. Area of the base is 256, or 16 squared. The perimeter of the base, that's 16 times 4, which is 64, times the slant height, which is 8√10. Let's run that into a calculator. We get 256 plus 256√10, which is 1,065.54 units squared. Now let's look at example 2. Find the surface area of the regular triangular pyramid. This time, we're given that the base edge is 8 on each of the 3 sides of the triangle, and 18 is the slant height. The first thing we do is look at the base, and the drawing has shown good practice. This particular triangle here is the base, and let me write on that a little bit here. Maybe I'll call this triangle ABC so I can talk about it. It's 8, 8, and 8. Half of this base down here is 4, so we get 4 right there. And then the height will be 4 root 3. Now, this is a equilateral triangle because our base is regular, which means half of it is a 30, 60, 90 triangle. And the relationship between the short leg and the long leg is short leg times root 3 gives the long leg. But you can also apply the Pythagorean theorem to get root 48, which is 4 root 3. So the area of the base then is 1/2 base times height, 1/2 times 8 times 4 root 3 is 16 root 3. This is our capital B. And then the surface area, this particular author did not write down the formula for surface area. It's the area of the base plus 1/2 PL. There's the area of the base, 1/2 P, which is the perimeter of the base, will be 3 times 8. And L is the slant height, which is 18. And we work that out and run it into a calculator, and we get 243.71. Now let's find the volume. Okay, for volume, we're going to need the height of the pyramid itself. And to find the height, we're going to need the apothem. So I'm going to make another diagram of the base. I'm going to make this one a little bit bigger now. Let me get my pen here. This is still the base. It's 8, 8, and 8. But what we want now is we want this apothem. If I draw in the radius, we see our right triangle here, and we have our Pythagorean relationship. This distance is 4, and this triangle is a 30, 60, 90 triangle. We need to be quite fluent with the 30, 60, 90 triangle. To get from the long leg to the short leg, I divide by root 3. So the apothem here is 4 divided by root 3. If you would like to simplify that, you can to rationalize the denominator. I don't think I'm going to do that. This is our apothem. So up here in the original pyramid, if we kind of think about a point here and that apothem, and then the height, we can pull that triangle out. So I'm going to pull that triangle out right here so that I can actually see the right angle. This is the apothem, which is 4 over root 3. This is the slant height, which is 18. And this is the height of the pyramid. This is one more example of decomposing a figure, pulling out that triangle. Now I'm running out of a little bit of room here on my screen because I can't show the whole piece of paper. So I think I'm going to slide to the bottom to set up the Pythagorean theorem. Okay, h squared plus 4 over root 3 squared equals the hypotenuse squared. H squared plus 16 thirds equals 300 24. Root 3 times root 3 is 3. So h squared is equal to 318 and 2/3. And then we have h is equal to the square root of 318 and 2/3. So now we can calculate our volume. Volume is equal to 1/3 times the area of the base times the height. Let's see if we had the area of the base. Yes, area of the base was 16 root 3. So let's plug that in. And our height here is the square root of 318 and 2/3. And we run that into a calculator and we get volume equals 164.90 units cubed. We're skipping example 3, so let's go now to example 4. Example 4 asks us to find the height and then the volume of the pyramid. We have the slant height given as 25. We have the edge of the base is 14. So the apothem is 7. And here's our Pythagorean theorem, 7 squared plus h squared equals 25. And there is a Pythagorean triple, 7, 24, 25. So the calculator gives us a height of 24. Volume is 1/3 base times height. So we run that into a calculator and we get 1,568 units cubed. We're skipping example 6 and now, or example 5, and now let's do example 6. A regular pyramid has a base of 56, a base area of 56 square centimeters and a volume of 224 cubic centimeters. What is the height? We write down our formula and we plug in what we know and bring down the letter for what we don't know. Volume is 224. 1/3 becomes 1/3. Base is 56. H is unknown, so we bring that down. Multiply both sides by 3 to get rid of the 1/3. Divide both sides by 56 to get rid of the multiply by 56. And H is equal to 12. It looks like our author did forget to put the units on here. 12 centimeters. Lengths are one-dimensional. Surface area is two-dimensional in square centimeters, and volume is three-dimensional. Now I'd like to do example 7. This is going to be a hexagonal pyramid. And I have a couple of diagrams that I pulled off the internet. The left-hand diagram here, it is a hexagonal pyramid. We see the apothem is lowercase a. We see the height is h. And we see the slant height is script L. And the base edge is also shown as B. And so we see the right triangle. In the second diagram, which is a different diagram I pulled off the internet, we have labeled the height, the slant height, and the radius. The radius and the apothem are different. So, example 7 says find the volume and surface area of a hexagonal pyramid with base edge 10 and edge height 13 meters. So, let's maybe put the numbers on this figure here. The base edge is 10, so B equals 10 here. B equals 10. And also the edge height is 13. So this edge is 13. The first thing we need to do is find the slant height. So I'm going to draw one of the triangular faces. Here is our triangular face. This bottom edge is 10, half of that is 5. The edge here is 13, and I do not know the slant height, and I'll use script L. So we apply the Pythagorean theorem here. Leg squared plus leg squared is equal to hypotenuse squared. And I think I'm going to let you pause the video and do the little bit of algebra to find L. L turns out to be 12 here, which is kind of nice. 5, 12, 13 is a Pythagorean triple. I know L. The next thing I need to do is figure out the apothem. So I'm going to draw a picture of the base. I like to work with hexagons because we have 6 equilateral triangles in here. And all these equilateral triangles are nice because they're 60, 60, and 60. This is the base now. And the base edge is 10. And I want to find this apothem. This distance here is 5. You should locate where your 30-degree angle is, where your 60-degree angle is. Of course, your right angle is here. The apothem is short leg times root 3, which is 5 root 3. So we now know the apothem. Now I'm ready to calculate the height. Using this top figure, you see the green triangle, apothem squared plus height squared equals slant height squared. And I'm going to pull out that triangle now. The apothem is 5 root 3. The slant height we know is 12, but we do not know the height. So we set up our Pythagorean theorem. A squared plus h squared equals L squared. 5 root 3 squared plus h squared equals 12 squared. And you can probably do the next step ahead of me. 5 squared times root 3 squared is 75. Subtract 75 from both sides. H squared is equal to 69. So h is equal to the square root of 69. Once you have the slant height, you can find surface area. And once you have the regular height, you can find the volume. So let's calculate volume. 1/3 base times height. Okay, now we need to calculate the base area. If we go to our reference sheet, on the back of the reference sheet or on page 2, we have the area of a regular polygon. Area of a regular polygon is 1/2 perimeter times apothem. So maybe I'll put that up here. Area of the base is 1/2 PA. The perimeter here is 10 times 6, which is 60. And the apothem is 5 root 3. So the area of the base, half of 60 is 30. 30 times 5 is 150. 150 root 3. Okay, now resuming finding the volume, we have 1/3 times area of the base, which is 150 root 3, times the height, which is root 69. Run this into a calculator, and we get 719.37 meters cubed. This is the volume. Now we're ready to calculate the surface area. Surface area of a pyramid is area of the base plus 1/2 PL. Area of the base is 150 root 3. Perimeter of the base is 60 again, and the slant height was 12. And we run that into a calculator, and I'm about out of paper here. And rounding off, we get 619.81 square meters. Let's take a look at the week 12 instructor notes. Okay, let's take a look at the scale factors. The scale factor is used to multiply times a length of one figure to get the lengths of to get lengths in the similar figure. Of course, if we multiply by a number that's less than 1, we get a smaller distance. If we multiply by something greater than 1, we get a larger length. To go from an area of one figure to the area of a similar figure, we do as follows. Given the area of one figure, to find the area of a similar figure, you multiply by the square of the scale factor. This is because both the dimensions, the length and width, so to speak, are multiplied by the scale factor. In the case of volume, given the volume of one figure, to find the volume of a similar figure, multiply by the cube of the scale factor, because volume is three-dimensional. Let's look at our examples. These are the week 12 similarity examples. We have two cones in number 1. We have a small blue cone, and we have a large kind of pinkish cone. This does have to do with surface area and volume. However, we are not going to be using the surface area and volume formulas. The small cone has a volume of has a volume of 125 cubic centimeters. And we need to find the volume of the second cone. I'm going to do this two ways. So let me get my pen here. One way is to take the volume, which is 125, times the cube of the scale factor. The scale factor here is 3/1, which is 3. So I'm going to take 125 times 3 cubed and run that into a calculator. I get 3,375 centimeters cubed. This is the volume of the second cone. The other way to do it would be to set up a proportion. Volume over volume equals 1 cubed over 3 cubed. And of course, we'll get the same answer. Now let's take a look at our second example. We have two similar figures again. Now, the thing that's nice about this generalization that we're using. It doesn't matter what the figures are as long as they're similar. They might be cones, might be pyramids, might be cylinders, whatever. This time the scale factor, going from large to small, the scale factor is going to be 2/6. The scale factor is 2/6, which is 1/3. So I would like to find the surface area of the blue rectangular solid. This is going to be 324 times the square of the scale factor, because surface area is two-dimensional. And if I run this into a calculator, I get 36. So we get 36 millimeters squared. These problems are not difficult. There are not multiple steps, but you just need to understand how the proportional relationship works. Our final example is a little more interesting because we have a little bit more interesting fraction. Find the volume of the first figure. So you can think about the scale factor. If we're going from small to large, the scale factor would be 7/4. Maybe I'll use K for the scale factor, would be 7/4. On the other hand, if we were coming back the other direction, the scale factor would be to multiply by 4/7. And we can do it that way because we know V2. So V1 is going to be the volume of the larger one, 2744, times the cube of the scale factor. And if we run that into a calculator, we'll get 512. So the purple volume is 512 inches cubed. Now, kind of for the purposes of note-taking, let's do this a different way. It's also the case that V1 times 7/4 would give us the larger volume, which is 2744. 7/4 cubed. And then if we divide by that, V1 is equal to 2744 divided by 7/4 cubed. And we know to divide by a fraction, we need to invert and multiply. So dividing by 7/4 cubed is the same as multiplying by 4/7 cubed, and we're going to get the same answer. I hope you found this video helpful. If you have questions, give me a call. Have a great day.